Hi, my name is Bob Grinier and I'm a volunteer with the Martin Fleischmann Memorial Project, so thank you for joining me this 23rd of January 2022. It's been just about a month since I last did a live stream, and since then a lot has happened. We got out a proposal to the 9 sites team who are doing the evaluations for fixing the Fukushima tritium-laced water out of the Alps system, and we have put a few things out which have been interesting. I don't know if people have been able to look at the papers that are in the book, which we are doing a one-to-one version of, and that is now half published and available for you to download at remoteview.icu. And we're going to talk about one of those papers today, which was quite a find when I came across it again, and I actually had to obviously read the text in detail. And one of the micrographs in there, I think it's going to be really, really special, because it just goes to show how observant Takkaki Matsumoto was way back in the early 1990s. I think it's a paper that was actually submitted on in, I think, 1991, if I'm not wrong. We can check that when we look at it. But in there, he not only identifies some sort of rope-like structures, but also he has a very interesting comment to say about them. And of course, in the VEGA experiments, particularly the ones that I shared some of the traces for of the what we call coherent matter traveling waves from the VEGA experiments of Dave, we have something that I believe is very equivalent. And over the last sort of 40 minutes, I've done what I've wanted to do for quite some time, which is build a quick 3D model, which we can tweak a few parameters, and we can see if we can create something that is akin to the traces that we see in real time. So it's only partly done, but we can do a bit on the stream today. I've also thrown a whole bunch of slides together. It's a little bit not perfect, but we can discuss the sort of aspects of the making and breaking. But what I'm going to be talking about here today is this concept of a reconstitution after the end of an Evo. And the reason I've chosen pasta there is because we have 3 different types of coloured pastas there, and you can imagine those has different elements that have been synthesized out of a similar structure that captured raw energy from matter and then reconstituted it as something else. But it's not just that. The reason I'm using this analogy is that if you can imagine durum wheat, you get this flour from grain, and you add water to it. You can imagine that the dried grain flour is the sort of ions, let's say, of some atom or whatever's the solid material in the original atoms that were captured are now in this sort of, whether it's the original atom or not, it doesn't really matter, but it doesn't have any electrons with it. And the water, you can imagine, is the electrons, and you add these 2 things together and they reconstitute into normal atoms, adding volume, and they present themselves in a form that is like the Evo as it dies. And we have seen things that look spherical, we've seen them that look toroidal, and we've seen them where they look like some sort of toroidal or interlaced woven braided mesh. And we saw that first in the work of Suhas Raukar, which I analysed from 2017, where we saw a near pure silver structure formed, and that was in a plasma flow discharge experiment where he was making his foil. We have seen copper, I believe it was, coming out of the aluminium in a ultra experiment, and that was coming through the side of one of the cones in the ultra experiment. And we have seen diamond structures, and we're going to look at a couple of those today, and then see if we can have a go at simulating that structure. So how is everyone? Can people hear me? If anyone can say yes, that will be useful. I hope I haven't just been talking to myself for the last 5 minutes. That would be not good. So if someone can see, hello Artifact, hello Corky, hello Brian Burwell, it's great to have you here. Okay, so we've got a yes from Corky. Hi, John. And so I'm going to fire away. Now, if you remember what I was talking about in making and breaking, and in many of the experiments we've shown, is when you get these plasma balls, these balls of fire, they have this double layer on there, and as I've described, things that are inside can be held inside but don't seem to be affected. But if it grows, it consumes material in the boundary of this double layer if it's at the right sort of coherence or resonance or something's going on, and it captures the material. And it seems to capture material, and it may be the case that some of that material is denatured and becomes other elements when the story is over. And so we've seen these areas cut out of the 10 yen coin or out of the copper plumbing pipes in Henk's experiment, where we had 2 fat iron plates, and we had these perfectly cut out areas just like we had in the Amasa gas versus 10 yen coin. And we've had a lot of these sort of spherical sections, and we've seen the spheres on the anode of the other VEGA experiments, both as individual, what the Sapphire project called tufts, but also wetting together into a large sphere, so you can get an idea of how these aggregate. And this is also what's happening in the VEGA Valley, the image you see on the back there, which I will intend to I will get around to launching the Kickstarter maybe next week, but if people wonder why there was some delay, when I arrived in Egypt for our pre-2020 style holiday, where it was just like normal life, to be able to focus on the Fukushima, I got off the plane and promptly left my glasses on the plane, so I wasn't able to see for the first 5 or 6 days, so I was forced to not work, which was probably a good thing. And so this is why I have these cheap $3 reading glasses that I got from a pharmacy in Hurghada. And I took an opportunity to go and see some of the structures there in Egypt. Definitely whistle-stop tours because of the distances involved. I'll talk about those in another presentation. And then we got back from Egypt, and I had the necessary infection a number of days after I got back, and my whole family did, such that I am now, unless they change the rules, which is something that can happen, have the ability to go to America. So I can do some scanning electron microscopy on the scanning electron microscope of Alan Goldwater at his Magic Sound lab in California, and I hope to meet with John Hutcheson. And if possible, if things work out, I have this sort of 75-day window now. I can come back and then go and, depending on how things are organized, visit John again and go and have a go with the Brown's gas generator if we can get that up and running in the intervening time. So there's a lot of other things I'd like to be able to do, but we need to get done what has been held off for some time now. Anyway, so right. So hi Rhett, hi Wild Man of the North. Hi everyone. Thank you Stephen Halls for joining us here today. Right, so I thought I'd choose this tricolore, I think it's torti, this double kind of spiral, this double helix structure, because many of the coherent matter traveling waves that we observed were of this type. So here it is. And so I want to talk about the very first time that I was really bemused about something that had occurred in a reactor. And this was with the Lion 1, actually Lion 2 core, because Lion 1 is actually still not opened. The actual core of Lion 1 is not open. So I'm now going to switch my mouse, and I'm going to, for those that are hard of seeing, I'm going to change my mouse pointer size so that people can see what I'm actually pointing at. And hopefully not do the wonky thing that I did some time ago. So cursor, and we'll make that a bit bigger so those people that need to can follow along with a little bit more ease. Okay, so Reconstitution after the end of an Evo. Well, let's start the story with what I believe was the source of some EVOs. And this is the diamond core in Lion 2. And a large sphere, so this is 10 microns. This is around about 27 microns, the same as the structure of the a number of cores of ball lightning that we saw coming out of the Vega Valley, if you remember, those FeO2 structures apparently. And this has, it's a little bit weird that in diamond, which is, as one might know, the hardest material known to man, with the highest dBi value, I think it is, and it has these diamonds, when they're doped and industrial like this, they are the world's best electron emitters, and so they have a lot of properties that were desirable for this type of experiment. But what we can see is there is a spherical structure. It has some substructures on here, which I've never discussed before, but I kind of wanted to. There's a substructure here, there's a substructure here, and there's a substructure here. But let's just focus on the big sphere here. Out of the node, this sort of pole of the sphere, you've got something else being sprayed out the back, and this is a common theme that you'll see in some of the other images that I will share with you, which I've shared in the past. But this is carbon, and this is something else. Now, it is light, and typically that means it's a heavier element. This could be calcium, or it could be nickel, because these were diapads, and so they had diamonds in nickel, and maybe the Evo had been formed and captured some nickel and then sprayed it out of the pole. But anyway, the material was captured inside the reactor, and probably a much earlier example of these kind of things going on inside the body of a mass of material is this kind of thing in a Hutcheson Steel Bar. And so this is a steel bar that was affected by the Hutcheson effect, and inside we have these spherical sections taken out. And we have observed this in the copper in the VEGA experiments with Henk late last year. We shared those images, but this is being cut in half, and material has been found to disappear from the inside. And this is a much more extreme version of the observation of the same kind of thing occurring in deuterated palladium by Takkaki Matsumoto, I believe, in 1990. Okay, so and we've shared this before, the yin yang, and so we've come to the conclusion that this is probably a half soliton, a phallico-soliton on the surface, where one is effectively the opposite of the other pole, and material is come out of here and slapped down on here. A more complete structure is this kind of monopole-like structure here, where the material has been captured from the core in the center here, and it ends up with a sphere of material left, which you can see on the optical image here, and that's why it slightly distorts with the refractive index of whatever the sphere is. Now, it might be a sphere of diamond, it might be a sphere of silicon dioxide. However, it doesn't really matter. It's probably diamond, amorphous diamond blob, because we saw those in the center of the Lion experiment as well. And so I'm just going to run a whole through a whole sort of series of slides here that kind of give some background. Like I say, it's not necessarily in the order that it should have been. I've just thrown them in here. So now, when these things are in situ, they're able to burrow and eat. So we've got a couple of examples. We've got this one eating, these ones eating in situ. This one as a kind of like half soliton eating in situ. This one eating in the core of the core. And then when they move, so we have some this one from the Amasa vibrator plate. I'm going to talk about a very interesting piece of data about the C.I.C technology, which I've wanted to talk about for a long time, and it's very relevant to the energy levels here. But specifically, the most important thing is from his patent, which was derived from the work that he did, and that is that the massive amounts of nuclear transmutations that he observed, predominantly to carbon and iron, which is interesting, and also to silicon, both of which Bin Juin Huang observed on his copper, and that we have observed on aluminium. But he also observed other elements that were synthesized in his Vachayev system. He calculated that the energy required to do the nuclear transmutations was actually only 40 eV, 40 electron volts. And so you can imagine that the coherence going on at the spot here, which if I go to the next frame, I probably have a slightly better image of it. The coherence that went on the spot here to create the coherent matter here that then exploded and then came out in this spiral form here, or maybe this is a soliton. This is a half soliton, and we've got one component here and the other component here, and this is the vortex loop between the two. It's one or the other. However, it's traveling along the surface and it's eating something along here. If that is only 40 eV, one can imagine that with the extreme cohering forces that we have observed in these ultra experiments, and obviously it was going on in the Amasa vibrator plates, and we know it must have been going on in the work of I forget his name now, Claytor and Stringham, but Stringham predominantly, and also in Leclerc. It has to have been going on, and in fact Vachayev made every element in the periodic table all the way up to bismuth using his technology, but of course it's much more gentle in the water systems unless you do something like Leclerc did. Anyway, so we're making our thing in our various systems, and ignore the piece of chaos over here on the right. What I'm referring to is the product of some of these neutral forms where they've captured the material and then they're dumping it here. And these are spheres of something magnetic that are dumped in a chain. So it's kind of like the whatever was going on in the center of the Lion reactor, and this is actually from Lion 2. So this is from the same reactor which this is from. So this is taken from the core. So the material is taken out of the core, maybe put into a neutral body, this micro ball lightning, and then it's gone through the core, through the copper, through the quartz, and then as it comes, this is actually the outside of the fused quartz. As it comes out, halfway through the fused quartz, it's dumped one sphere, half in and half out, and then it's dumped two more spheres that are kind of like magnetically aligned, like those kind of little magnetic neodymium balls you can get as a toy. They're joined together like this. So I imagine that this is iron, and we know that these systems like to produce iron in their core, and so I imagine that's what it was. So that's kind of what I saw there. And then we know from other aspects of Lion, in other versions of Lion, that we have norths can join with norths, and we have souths that can join with souths here. And in fact, that's the other way around. I think this is a south, and this is a north and a north. But anyway, it doesn't really matter. One's one and one's the other. But you have two of the same type. So we know we've got a higher white spot here and a higher white spot here, and the strong ring around the outside. And here we have the black spot and the black spot, and it's just more diffuse over the outside of the perimeter. And we know then also that they don't just group into necessarily twos. They can group into more than that. And here we have a number grouped together, here 3, and they're actually all of the same type. So that is that. And we've talked about that in the past. And here is your magnetohydrodynamic structure. And when you look at this on the front side, it actually looks like it has a cluster. So it's two together, but it almost has its own sort of diachron instabilities, even though this might be a phallico-soliton here. The actual substructure in here has got much more going on. And the first time we saw something that might be physically representing this in a plasma form was in December the 4th, 2018. I was talking about HHO and plasma spark plugs. And I'm sorry for forgetting the name of the person that spotted it, but you can go to my Steemit blog. And there was this thing that appeared away from the actual plasma spark plug. And it seemed to have a bit of a substructure to it. It's difficult to tell because, of course, you've got JPEG artifacting in there, and that might have been playing a role. But it's very similar to the sort of plasmoids that were later, and this was actually from a video from May the 2nd, 2016 on ignitionsecrets.com. And if you go to the next frame, and I've talked about this before, this is about the work of Bogdanovich et al. That was published in 2019, sometime later. And this was again with a plasma flow discharge, but in a different system, such work that they were doing since the late 1990s, early 2000s. But this was recent findings. They found that they saw these plasmoids, and in this case they say a luminous toroidal object, and it's going and translating over a surface, and that's these things can cluster together into structures, bigger structures, and they've got this apparently on video as well. The stream of electrons from the dielectric surface and complex object of type of luminous rings that is formed by it, rotating around its own common axis and rolling on the surface. So, yeah, so the stream is formed into a set of several rings, 5 or 6 of the same diameter, which rotate around both their own and common axis parallel to the plane horizontal. So you have these rings and they're rotating around their own axis, but they are also, the collective is rotating around and translating over the surface. So based on this and a lot of the other sort of plasma tracks that we have seen, I'm going to get rid of my mugshot there so you can see the whole frame. Yes, so just the last couple of slides, line there, this one, this one, and this one, and this one. Okay, so what is going on in one of these structures, and is it really a toroid or is it a sphere? Well, I've talked about this, which was from the 1973 patent of Paul Collock, and it is a torus with poloidal and toroidal fields and electric currents in there, and that this forms a sheath around the outside. So this is actually a toroidal thing that creates a spherical overall type of structure that has 2 poles. So this kind of speaks to many of the things that we've observed. This has got a suppressed pole but a focused pole down here. So this might be a group of these structures grouping together, because we know they can group together. Okay, and this might just be a pair, and this could be groups forming a mesh-like structure, as we observed in the thing in the VEGA experiments, and this is maybe a group or an individual structure. But anyway, Paul Collock structure here, and we saw some similar things on the plasmac structure type things on the inside of the NOVA reactors. So you've got this divided section here. Now, remind me to talk about this when we come to the simulation around the outside. And then we've got the thing that looks like it's spinning in one direction around this axis. And so I kind of imagine that this spinning here is this kind of going on here. And then the outside is this kind of double layer area. And so is this describing everything? And what it is that I think when this crashes into the surface, it splats onto the surface. You've got the double layer around the outside, which has its own wave function. And then you've got the core that's spinning it around. And as the dome of the material crashes onto the inner core, it still gets shifted before it freezes in place. And so we saw something similar to this in the supernova reactor inside the wall, where you've got this field on the outside, you've got the double layer and the core, and this was extremely similar to the type of structure that Matsumoto published in his 1993 paper, and it's almost exactly the same scale. It has the same core center. It has the almost the identical structure. I mean, it's almost like a carbon copy. This is silicon, I believe it's silicon dioxide splatted onto the aluminium background, and this is whatever it is in his particular thing here. Rings on black back surface of nickel foil with sodium chloride solution, macro explosion ring. Okay, so I'm going to switch to a different presentation here, because I just want to talk more about the coherent matter waves. So I'm going to go and drop in a couple of slides to talk about from the coherent matter wave part 2 presentation that I gave in Sochi, not Sochi, in Assisi. And here it is. And you can see a range of these forms here, where these sort of bizarre M&M tracks, and this maybe is an M&M type track. These you can kind of imagine as, I don't know, but maybe we can see what they could be. And this looks like maybe one or two structures orbiting around each other, and they seem to be interlinked. And remember, when we were looking at the structure from Bogdanovich, it really, each of the torids, they seem to be communicating with each other or linked to each other. So it's not surprising that we see this in a smaller level here. And within this presentation, I showed that this, where potentially you were getting the same kind of spiraling structure being formed with the coherence of HHO as it goes through this carbon capillary, and it gets forced into a toroid through shear forces, and you get the cohering in the center, forming this beam here. And this was very similar to work done in published on the 17th of June 2020 by Anatoly Klimov, but these were old massive color slides, photos that were taken of a plasmatron. So this again is going through a capillary, and it's making these structures. And in this case, you can see it looks like two are coming in here, and it breaks into two that are also spiraling away with their own kind of periodicity. This one is coming through with its periodicity as well. This one has a different periodicity. So something's going on in here, all kinds of shear forces and whatever. And it's producing these plasmoid structures which are coming out, and in this case you can see that it's dividing into two other plasmoids. And this, if you hold this concept in mind, this is very, very important when we move forward. So these are ones where I've showed you where the balls are forming on the surfaces, and then we found out about these ones doing all these funky business. So you've got two orbiting around each other here, and you've got a big fat one here. And so these are about four or five frames, maybe 6 frames linked together. And so my question is, are we looking at something which has its own orbits, and what you're seeing is effectively a persistence of vision? So the model that I'm going to present to you today, that I made in the 40 minutes before I started this presentation, I believe may account for what's going on, at least on a sort of sketching it out basis. And I think that if we can get the high-speed camera on the work of Dave in Canada, and so I need to get a very expensive high-speed camera on that job. So we wanted to get it for a while, so I think we're going to go and get that. And Dave will run some experiments. And what I want to do is effectively time slice this, not 1/60th of a second, but maybe 1/1000th of a second, or 1/5000th of a second, so we can actually see what the actual substructure is, and trace its path with more fidelity. So that is the aim, and I'll probably be talking about what Dave has been doing later next week, which is moving us in the direction ready for capturing these kind of traces. And so I showed this in the past, where you can see one down here, all kinds of extremely fast traces, but I've captured them here. So spiral. So you can see where my pasta sort of noodly goodness came from in terms of the kind of inspiration for what I'm talking about here. Now, the one at the top here I think is very interesting, and there are a number of traces that look like this. And I think this one is also very important. This actually looks like it is a tube. And why would that be? It actually looks like it's a tube, but it's cut off at an end, almost like a copper pipe. And so this almost looks like it's a torus that has no other rotational movements. It's just got a translation. And so this gives me a hint that probably a lot of these are tori. And we know that the witness marks, certainly with the iron on the copper oxide in the Henk experiment late last year, that was definitely a torus. And so now, are they all torus? Well, certainly Shoulders and Dr. Takkaki Matsumoto said that they're tori or spheres, and we've explained why. So the same reason Tesla used torus or spheres for his the balls or tori at the top of a Tesla coil. It's because of the minimum surface curvature and single surface. This also could be a torus, interestingly enough, but it's about the rotation going on and the phase of the rotation, and I think we'll be able to investigate that a little as we go through this presentation today. What else? So I've got some close-ups here, and I argued that in this case you actually had potentially a negative structure and a positive structure, like your yin and yang in the bull burn sample from 1986 from John Hutcheson. But the yin and yang are orbiting around each other, and because one is attracting ions in the whole time, let's say, it's always glowing, and the other one is pushing a wake of electrons in front of it, you are getting it only when it's coming towards the camera. It's like a wake in front of it, but you don't see it when it's rotating around this side. Okay, but it's like a positive and negative structure orbiting around each other, producing this kind of trace. Okay, so and that's the video from that one. And I have shown how we have seen, this is in Solin's 2001 patent, and he actually had this. And you can see it's going round, and then it goes round, it sort of goes round itself. Now, I think in my model, you may see how this can appear. And you've got the same thing here in very large Hessdalen ball lightning. So this is looking down on a valley. There's a treetop here. So it's a very large area. The ball lightning is already disrupted. It had hit a tree over here, and it had partially disrupted into this M&M track. And then it hit another tree, and then it had a different periodicity as it came through and to this point. Okay, and then this one down the bottom is a ball lightning track that was taken by our friend in the Outback, and I joined the frames that he sent me up, and there is a little gap between the frames because of the sample on and sample off time for the camera that he was using. So you can imagine this is a relatively continuous trace, and this is one from an old book by W.R. Corliss of how ball lightning should look. And then we showed in extreme interactions that if you have some of these things flying about, they can actually join up. They can influence each other's motion. And so over here you can see where one has joined, another one joined here, then we had another one join here, and we had three going together. And so they do influence each other and so forth. So that's probably all we need to do. This is a trace that was shown in 2015 by Jean-Francois Geneste. He was, I think, former Airbus chief engineer, and he was at the EADS colloquium in 2010 that this was made, this Claude Deveau. He recorded this trace, and we created something very similar here by compressing in the linear direction the trace coming out of one VEGA experiment here. So I think that's probably all I need to do for these traces. Oh, no, I want to show this one. So this is quite important because we're going to, this is a bit of noodly goodness that I think we'll try and simulate this evening. And this was similar to a trace observed by, who was it? It was, oh God, sorry, Baranov in Russia. And the key thing here is this video up here. In fact, it's so key. I'm going to step away, and I'm going to blow that up so it's full frame, because this is probably the most important sequence of the day. So that we need to address with in comparison to what Takkaki Matsumoto wrote in 1991. So here we are again. I've just blown this up. This is a GIF animation. You can go and get this off of remoteview.icu. And what you see is something over here. And so we have this crack between the two brass plates. And this is to cause electron bunching between the cathode, which is down there, and the anode. And this is causing an intense explosion here. Which we know now is likely this Coulombic explosion from the ball of fire, the itonic cluster, the Evo, the macro Evo structure. It blows up and then something gets shot out. So the speculation was that this structure, whatever it is a subcomponent of the thing that just blew up over here. And it's flying off with the relative motions and momentum that it got from the explosive event. Okay. So I think we'll go back to my main presentation. I don't think... I'll just put that to one side. Oh, I wasn't showing you that, was I? Oh, was I? Was I? Yes, I was. Okay. Okay, going to be a little bit out of order here. So, we've shown that even with HHO, you can produce a coherent sort of sphere with a double layer. This is the double layer on a sphere inside a Henk VEGA experiment. And this is what was in the paper in the Journal of Plasma Fusion Research. This is a model of a fireball from January 2001. And so they're only talking about this hemispherical type structure fireball, which you see all over here on sapphire reactors and so on. And here's an example, and we showed some clustered ones there earlier. But here, because of the configuration of this strip of nickel here, we have this full sphere on the end, and so this is really what it wants to form if it can. Otherwise, it forms something like this on the on the surface. Now, you can imagine maybe that there is a half soliton in here, and that this is a structure here. Now, I've never really discussed this before, and maybe it might be the right time to do this here. So let me just find something on my blog, which I think is relevant to talk about here. Is it on this one? No, it's not on that one. Bear with me. Okay, yeah, I don't think, maybe I did discuss it at the time. Okay, yeah, okay. I don't think I did, actually, but it's always sat in my head. So it's on VEGA disappearing nickel, and this is also where we have this image, and you can see how it's going through the other side, and you've got the double layer on the outside with a bright sphere. And I said this, and this is how they're kind of wetting together. But in this image, what I did was I contrast adjusted the video, and you can see the outside of the double layer, the inside of the double layer, but it would appear that each of these spheres has two bright spots on them. So we got two bright, and they're not always in the same place. Now, it might be that there is more, I don't know, but we got a bright spot here and a bright spot here. Here we got a bright spot here and a bright spot here. Here we got a bright spot here, bright spot here. It's almost the anti-node of this. These ones, you can't really see it. This one, you got a bright spot here and a bright spot here. This one's, you got a bright spot here and a bright spot here. And these, you know, are they connected to each other? I don't know. Or do they have their bright spots directly opposite? So I don't know whether you have a pair of structures here, or this is some sort of factor coming out of a phallico-soliton. So maybe if I zoom in, you can see better what I'm referring to. It's these two spots, and I always found this a bit curious. As you can see them here very clearly, two spots. So it might be that in the case of the one that's at the top here, the two spots are kind of either side, and you actually get the full torus. It's like one's there, and the spot is coming around all the way around and come to the other side somehow. I don't know. it's kind of like, this is an open question, and I would like people's opinions on it. Yeah, so what are these two spots that are on this structure here? What are those two spots? So get your thinking caps on. What are they? Okay, so I'll forget my diversion and I'll come back to where I was in the presentation. So, okay. Okay, so now, what do these things do? What do these things do when they are collecting material? Well, they kind of eat it. They eat these channels, and they seem to throw things out of the back. And in my Sochi presentation, I sort of went eat. And what it was, there was a 7 centimeter or 8 centimeter, something like that, section of quartz. And there was, I think it was like a 20 micron channel that had been bored all the way through. And periodically, there were spheres and actual crystals in some place of different elements, it would appear, being dropped down. And annoyingly, Vlad Zhigilov, in the presentation that followed mine, had observed something similar in his experiments. And it's kind of like I watered his firework, let's put it like that. It was kind of like, damn! It's like one of those moments in time where you go, no! You got there before me. Anyway, so the point is, it looks like it's moving in a direction consuming material. Now, let's say it's a torus or a sphere, and it has a double layer on it. It consumes the material into the double layer, but it seems to throw things out of the pole. And when it dies, it seems to leave things in a sphere. And so where have we seen that before? Well, we've seen it here in the work of Takkaki Matsumoto. So this is from his, I think, 1997. Here we go. Experiments with a lead wire in potassium hydroxide. So there's no carbon involved, and it sprays carbon out of the pole. And here is a more extreme version that we've shown before. So lead is 204, 206, 207, 208 nucleons. Carbon is 12, 13 or 14, not likely to be 14 because it's radioactive. So 12 or 13. So you can get a lot of carbon out of a piece of lead. And Solin said that it forms spherical or cylindrical tubular bodies, and you can imagine that the tubes are just these wetted together sphere electromagnetic Evo mesh structures. And here, and it says it forms these hollow balls, and out of the hollow balls you get the transmutation material, which is exactly what was observed by Takkaki Matsumoto. Okay, and we've also observed spheres as a resulting product here on the tungsten exposed to master gas. So it's eating these channels. The plasmoids are eating the channels partially under the substructure of the tungsten. And then at the end of the channels, you end up with these spheres, these spheres, these spheres, these spheres. And the spheres are where you have the other elements, okay? So the ball that's left is the thing that's the other elements. And we've spoken about that a number of times in the past. And then we've also spoken about the Amasa gas on the surface of the 10 yen coin. So in this structure, which is a yin-yang, we have another yin-yang, and in this yin-yang, on this side, where you make stuff, this is the break, this is the make. On the make side, you have this cobblestone area here, which is nearly pure copper. And of course, it would be because of its magnetic nature. And then on the surface, you have copper oxide, which has obviously oxygen. And as we saw the plasmoids moving around on the Bogdanovich work in 2019, this was in 2019. And these are, in my view, plasmoids that are moving around on the surface. They're consuming the oxygen and they are converting it to sulfur, which you see down here. 2 oxygen isotopes go to sulfur isotopes. And that is what we observe on the actual miners when we look at the reference and not on the control area. So this is these. Now, I don't know whether this happened nearly instantaneously or it happened for a period of time after the experiment, because it was some months between when I did this, I think in May or whenever it was in Japan, and putting it under the microscope at Alan Goldwater's Magic Sound Lab. in, I think it was September in 2019. So these might have been active for a number of months, moving around and converting the material. And it might have been the case that if I put it straight under the microscope, I wouldn't have found this. So I don't know. It might have been something that was only possible to find. And in fact, actually, if you look at some of these areas, and I'd like to look at this again, it looks like it starts here and then it goes along and it kind of builds and it breaks and there's kind of a branching going on. So I'm quite keen to actually look at this again and study this in a bit more detail. So this is something moving along, consuming it. Was it a torus? I don't know, but they're spherical globular type structures that have been at the end. Now, in the case of the Amasa versus gas plus titanium versus PTFE, there's a number of things that were important. Within this structure here, there was... no, that's the wrong slide. This one. We had these cones and rods. Cones and rods. Cone, there is a cone, and you have a cone and a rod. And at the base of the cone, you have nickel, then it's iron, then it's chromium, then it's titanium, and then you get a carbon nanotube coming off the end. And so it's captured the carbon from the PTFE, and it's in the Evo. And this is what I'm talking about. It gets material, it carries that material to another place, and then it dumps it. Matsumoto talked about this new type of electricity and the fact that the microball lightning could travel along a copper wire, and then it disrupts, and it left carbon deposit on one end of the wire. So it's able to carry material from point A to point B. But if it's also grabbing some of the secondary material, in this case the titanium, and then it then dumps. What it's dumping down is based on the intensity of the material within it. It is it's kind of like nickel, iron, copper. Nickel, iron, chromium, titanium, and then carbon. I think that's the way in which it goes. And so it's dumping levels of alpha. Like triple alpha, dual alpha, single alpha, and then just dumping the carbon at the end after it's lost all the remaining titanium atoms. And so one is about a pressure relationship, and another one is about how should we put this? If the whole thing is coherent. So what we saw with the perfect silver in Suhas-Rao cars, and with the copper in the Ultra experiment, and the diamond that we'll look at in a minute. Those, I believe, are where the whole structure is resonant and it basically dies instantaneously. So the whole thing leaves what it had at the point it dies. But here's a slide which combines a number of things. I think this is on the inside of a tokamak in Russia at the nuclear physics laboratory there. And this is like sorry if I actually show it, that's helpful. I've shown this slide before about the Sumerian tree of life. And the fact that some plasmoid has hit here. They called it in this particular work, if you go to the link here, unipolar arc. But unipolar arc is basically the same as Messiat's ecton. It's come here, it's branched into 5. Note that 5, that's the same number as is reported by Bogdanovich as a cluster. And then the 5 has gone out and it's consumed, it would appear, some of the tungsten, the fine tungsten structure here. And is this converting it to carbon? Well, it probably is, given that this is an SEM, and typically this would be a lighter element, and we expect it to form carbon. And this is the same thing that Shoulders had shown in 2004, and it's the same thing that Lion has shown in when we analysed the inside of the quartz in Lion 1. And so you have the plasmoid running along the surface, and I would imagine that this is dumping out carbon as it's doing this, or at least it's changing the structure of the material. And then at the end, you see the thing die. At the end, you see the thing die. Now, something came out as a substructure here. This was probably the original one here, which broke up into 2. Then this sort of carried down and so forth here. So now... probably one of the most extreme examples was in the plasmoid that went into the tungsten, which almost teleported into titanium, which kind of this is a bit of PTFE and titanium combined. You can see here when I look at the material on 262 has a high level of titanium here. but it's also got a high level of fluorine. Somehow it's a mix between the two, and it happened instantaneously. But here you can see the plasmoid is burrowed in, and as it's burrowed in, it's churned things up, but it's also transmuted the elements. So in 260 here, you can see 260, we've got a wide range of elements. We've got iron forming, and we've got calcium and potassium and chlorine and sulfur and phosphorus and silicon and aluminium and magnesium and sodium. And all we had at the beginning was titanium, fluorine, carbon, oxygen in the air. Okay, so it's synthesizing all these things that come through. And this is, I believe, where it died. And you can see it's got bigger. This is our pasta, our durum wheat, regaining the water, the electrons. And that is the point that I believe we had the explosive event that led to a lot of the other things going on. And you can see it here blown up in bigger. So it's burrowed in a continuous width channel, which you can see is 20 microns wide, the same width as the channel on the lion fused quartz that I was talking about earlier, that was dumping material behind it in spheres or crystal form. And then it kind of died here. And just for reference, if you want to know where that is, here's the crystal area here. This is the point here, and it's in this area here where this plasmoid came in. So it's all in line. I think it's here actually. It's in line with this, and this how this bit of mixed PTFE and titanium landed a distance in from the edge which contacted this, and this is titanium oxide. It's like teleported this piece of polymer inside here, and then it exploded here, and this was the shockwave. You can see the shockwave and the shape over here. There's multiple shockwaves gone on, and this is this Solin instantaneous coherent nuclear transmutation process going on. Okay. So in summary, we've also got, we got this one. We've got the half Solaton structure here doing transmutation. We've got the balls going around. We've got our rods and cones. But also, I didn't discuss this one here, but we have probably a spherical transmutation area underground here, with under the surface of the indium here. And it's exploded like a magma chamber in a volcano, raised up the surface of this, and out of it we've got this carbon plume, this silicon carbon plume coming out, almost exactly like was observed by Matsumoto in 1997. Okay, so that is kind of the background. So, I've talked about how, so I've said you can get spheres coming out of this. You've got spheres here. You've got, where is it? We have, where's that one? So we've got spheres there. Obviously, we've got spheres here. We have spheres in the tungsten, wherever that is. I had it earlier. There's spheres here in the tungsten here. And right at the beginning, I talked about these spheres that we saw coming out of the inner core, these magnetic spheres coming out from the Lion 2 reactor. Here's one, though, which is very interesting because it is from, and I've talked about this before, it's from the core of the 225-day reactor of Alexander Parkhomov, Dr. Alexander Parkhomov. And this is like fluffy carbon. These little stars that you see in here, which you may not be able to see, but you can download the PDF of these slides when I'm done. These are little bits of nickel. There's a bit of the nickel PNKO2 here. So carbon is this color, which is 12. Nickel is here, which is sort of in the 60s nucleons. And this could be calcium. The reason is because it's between carbon and nickel. And we know that the Parkhomov reactor produced a lot of calcium. Now, whether it was coming from fusing other elements, as we know calcium can be produced by Lena, or whether it's fissioning from the tungsten, as we observed in Amasa gas on tungsten, it doesn't really matter. What's interesting here is that we appear to have spheres. And rather than individual spheres, we have a chain of spheres, which is, in a way, similar to what I showed you at the beginning. Here, we have a chain of spheres. So it's like the plasmoid dumped physically a sphere, and then a sphere, and then a sphere. And that's what was happening in the tungsten as well. But in this case, it's like there's two spheres, and then you can see they're twisting. They're twisting, so they're like side-by-side spheres. So I believe what's going on is that you can have one or more. We know from here we can have clusters. Okay, so if you can imagine a fragment of this cluster broke off, which had two structures linked together, okay, and they span off at a velocity as one of these blew up, and then as they were dumping the material that they had collected in them, they dumped this, and they had some rotational and some translational moments on them, but periodically they resonantly dumped a whole load of material, and then they moved and dumped it. So the whole structure is neutral. Now my question is, are these spheres hollow? Are they hollow, or are they dense, solid? I don't know. I imagine they might be hollow, actually. They might be hollow. So it's kind of like the pairs, and it kind of like, it's still neutral, the structure, but it's kind of shedding a whole, it's kind of like a snake shedding its skin, if you can imagine. So again, just to say that again, you have this kind of structure, but it's clearer done on Bogdanovich. And these are either toroids like this, which they're saying they are toroids, or they're spheres, or they represent as spheres because you have a toroid in the middle and it's producing the sheath around the outside that presents itself like a sphere. And this blows up, and a fragment comes off with a range of imparted velocities on it, and then it dies. And what it does is it goes along here. Now maybe it's neutral and it goes off and it carries on eating more material and it does this same thing somewhere else. I don't know. Or maybe this was all of the material it had in it, and by the time it got to here it was just alpha particles, and it like it did when we are looking at this. I believe that after it's dumped your cone, and then it's dumped the carbon nanotube, you end up with just alpha particles. And in fact, normally it would just be one alpha particle. So you get rid of the material you're carrying plus the transmutation alpha conjugate nuclei. Then you get the material you're carrying. Then you just get the predominant alpha conjugate nuclei, which is carbon, 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 carbon. And then at the end, you either get a beryllium atom, which decays to two alpha particles, or you get an alpha particle. So you either get two helium atoms coming off the tip, or you get one helium atom coming off the tip. And so is that what is occurring in this structure here? I don't know. Okay, so in this one here, this is the combination slide which I shared first at Azizi. And so we said we had a coherent matter structure forming, and then it blows up, and then you get this braided structure coming out here. And this is 1/60th of a second, this is 2/60th of a second, this is 3/60th of a second. What I want to do, I want to be able to look at this in 1,000-second slices. Or I want to look at it in 2,000th of a second slices to know whether what we are looking at here is a what do you call it? A sphere or a torus, and whether they have rotational around their own axis and around the common axis, and that this is maybe 1, 2, or 3, or whether this is one torus. And maybe we're going to get a clue from what we show in the simulation, which I made in the 40 minutes before the presentation. And again, you have these repeating patterns, repeating here, repeating here, repeating here, repeating here, repeating here, repeating. This is why you call it coherent matter, because all of the matter is acting as one thing. But it's a traveling wave. It's not only a wave in its substructure. It's the whole thing is a wave, and then it's got its own imparted movements on it, and so it's traveling out here. And this is what it's doing when it's interacting with a piece of material in the steel plate on the Amasa vibrator plate, and here is a dead one. And so, like I'm saying, it can leave spheres, or it can leave groups of spheres in a single line, or multiple spheres, if you've got two, or let's say this is two structures orbiting around each other, like we showed in some of the other traces, it then leaves two, or maybe this is multiple. Maybe this is multiple that are orbiting around here. But whatever, it was clear to me that this was the explosion of a coherent matter structure, and that this is the aftermath. This is what happens when an Evo dies. This is what happens when an Evo dies. This is what happens when an Evo dies. This is what happens after an Evo. Okay? This is making an Evo, this is making an Evo, this is making an Evo, this is making and breaking. That's the death of an Evo. It's the sphere. And I've shown other Hutcheson samples where we have a similar structure and we have like another type of sphere. It's not clear. Maybe it's carbon or some sort of metallic structure. This is the damage of an Evo on a surface. This is an Evo in motion. This is an Evo in motion. This is an Evo in motion. This is an Evo just happily living where it's resonantly happy to live, given all the parameter space in there. This is the death of an Evo, death of an Evo, death of an Evo, representing as different elements here. This is an Evo as it died, it spewed something out. This is an Evo as it died, spewing something out. This is an Evo as it died, spewing something out. This is an Evo doing work on the surface. Okay, so I think you kind of get the idea. Any questions at this point? And then I will go to my simulation. We'll see if we can have a bit of fun here and create some pretty pictures. Any questions at this point? Any questions? So I'm gonna prepare the simulation. Yeah, I think that's all I wanted to say at this point. So give me a second. Right, we don't need that. Okay, so is Evo production during HHO electrolysis desired? Yes, Charlie. Essentially, you will get them in a number of ways. The two principal ways are a cavitation bubble forms and then it collapses, and you will get, as the cavitation bubble collapses, you will get a reentrant jet that will create the intense coherence at the point that the reentrant jet hits a more solid piece of material. The other way is through resonance using sound. I believe that sound resonance is the absolute critical aspect in many of these technologies. Now, sound can be all the way up to kind of vibrations in matter, phonons, and so you're going to get some resonances going on even in that scenario. I'm going to be talking about this more in next Saturday's APEC presentation. It's something that I wanted to say since even before Sochi in 2018. I've got to make that presentation. I've got to do my taxes next week, so it's not something I can discuss today. But yes, you want to be doing that. Reversing ball lightning might prove a challenge. I'm not sure what you're trying to say there. You're going in the opposite direction. It depends whether it's charged. You mean unball lightning a ball lightning? Well, it does that. It's all by itself. You're unlikely to get out of a ball lightning exactly what you put in, because you know that because of what it's doing. So. Yes, trumpets of Jericho. Yes, Corky, exactly. Did I buy 2 pairs of glasses? No, actually, the pharmacy only had 1 pair of glasses, and this isn't really my prescription. It's just I can get away with working with it. So we're going to sort that out at a different time. Cube-centered elements under pressure. Well, it's definitely under some kind of pressure. Vacuum pressure, I would probably argue, of which probably gravity is the same thing. It seems weird, vacuum pressure, because people think of, I mean, the physical vacuum, not like vacuum, which is physical. Anyway, I think you guys know what I'm talking about. Okay, so let's have a crack at this simulation, which I have done. Well, I haven't done. I just started it because I thought it would be fun to do a little bit more. Will the HH electrolysis for fuel create radiation? Well, what you're looking at here is strange radiation. It is coherent matter traveling wave beams, as I understand it. Currently, I'm open to that all changing when better data comes along, but that's how I believe it is. And those can go inside you, and yes, they can kill you. But when then the thing has done its work, the products are generally not radioactive. Where that falls away is that you can use sound and cavitation. If you drive it on the same spot resonantly, you are going to create all of the elements in the periodic table, and this is what was done by Vychev, and it was also achieved by Leclerc, and so he actually went through into radioactive elements, and so did S.V. Adamenko, but with a different technology, electron relativistic discharge. You don't want to do that, and so probably one of the most dangerous things that you can make, which are high risk devices, are a hydrosonic pump. They will create excess energy, but they'll create dirty water and enough strange radiation and normal radiation to kill you, because it synthesizes very heavy elements and then they fission, and the flux of radiation can be extremely high of both normal types and strange radiation. So that for me is the fastest way to die. And there's a risk from any spinning body, and I'm going to be translating the work of, I've been given permission, of Alexander Shishkin. So probably into February I'll start putting that out. There's so much to get out. There's some excellent work that Dave's been up to. So I need to get that out the door as well. So, but Shishkin's work is really important in this respect. Yeah, I mean, the point is that using so Rhett Oracle has said was thinking about using Sony Soundwave software to analyze. Absolutely, I analyzed in fact it was before we saw the cavitation spots on day one of being with Roshin Amaza that we put sound detectors, both an ultrasonic 384 kilohertz mic and a much lower capability hydrophone into his vibrators, and immediately we observed that there was ultrasonics going on. And so it's just surprising that, you know, he had the patent from 2000 or 2001, and here we were in 2019 establishing within a few hours of arriving that it was producing ultrasonic sound. But that's not relevant. In fact, you could have sub 1 hertz, but you just need a resonant structure, and then on the, I think it's the antinodes off the top of my head, you will get the coherence forming, and this is something that I'm going to talk a lot about in the APEC presentation. Okay, so I'm going to go ahead with this. So this is Lightwave, and for my sins, I was the first registered trainer of this software, which was originally in Newtek's Video Toaster, and I was the first one of two, me and my former business partner, in the UK training this software. So I'm a little bit rusty. I hadn't used it for since I did the basic 3-tier Evo and the Pintac field structure of the monopoles in the last year or two. Those are the other 2 times I've used it, but I cracked it open today for 40 minutes before the presentation. And we have a toroid. It's not the most incredible modeling object I've ever done. And we have a sphere. So there we go. We've got a toroid and a sphere. And those are the 2 structures that we are interested in here. And what I'm going to do is I'm going to put this into a little bit of an animation, and I'm going to pull it up now. So we'll get rid of this. We don't need this. And we'll go down there, and we don't need that either. So here we go. This is our simulation. And what I've done is at the bottom here, you can see I have this tori. And maybe if we go to the top, you can see that this is a torus. There we go. It's a torus. Okay. And if maybe I put texture shaded wireframe maybe. Okay. Anyway, there we go. And we can go to our side view. So that is our torus. Anyway, I'm going to go to the camera view here. And what I've done is I put some rotational motion onto the torus. So it's spinning around its own axis. And then I've got some other spinning around the common axis. Only in this case, I don't have a second torus. I've just got an off-axis spin. And this is the basic structure that we can imagine here. So you can see what I'm doing here is I'm spinning it, but I'm also translating it. So this is our traveling wave. Our wave is our Solaton, which is our toroidal Evo. And it's spinning around its own axis and spinning around the common axis, although in this case I only have one in place. So this is kind of the case for something where, you know, maybe something is, how should we put this? It's got an evil twin. It's got a positron evil twin, which we're not seeing. So it's orbiting around the center point of mass for the evil twin positron. Okay, so and I can actually I pull this down here. I don't need that whole frame. Come on. I have a couple of other things I can control here. This is some parameters which I'm going to control in a minute. Or one parameter, which is useful. And what else do I have? Yeah, we'll have that one up. Okay. All right. Good. Okay. Non-modal windows that cover over each other. Not very useful. Okay. All right. Is everyone with me? So we got that going up. Now I'm going to go in the camera properties. I'm just going to change the camera properties here. If they come up, where are they? There. And I'm going to turn off the motion blur here because I don't actually want any motion blur. I'm going to show you what I've done to the surface here. So I'm going to take a perspective here. And I'm going to switch on the rendering here. No, not that one. This one. Okay. And that's because I'm still doing... What am I doing? Okay. It's because I've got the luminosity. So I'm going to have to turn the surface down here because it's too luminous. So just give me one more. I need to pull up one more window. Here we go. Right, I need to turn the luminous. It's at 5,000%. Let's just turn that down to 100. Okay. Now, what we've got here is our double layer on our torus. Okay. And this is created in this software by creating a gradient, which allows us to say there's not a lot of thickness. And what's happening is we are looking through the normal to the surface, to the camera, or to your viewpoint. And on the edge, we're actually looking through the double layer. So this is kind of what we see in the VEGA experiments. I can make this double layer bigger or smaller. It's not important. But I'm just saying that because we are looking through the edge, we see more of the structure of it. And so we actually have a thickness. Now, if I actually swap that out for our sphere, now I've not got enough space on the screen, have I? Okay. There's our sphere doing the same business, yeah? Okay. So this is our spherical Evo, and this is our double layer on our spherical Evo. And if we go here, we can turn on. So there's our two structures. Okay. So you can see when it's presenting at this angle, I'll get rid of the sphere for now. When it's presenting at this angle, you're seeing through more surface areas. So you end up by seeing a different structure as the camera views it. Now, why is this important? Well, it's important because I believe that this will help us to achieve what we physically see in actual things that you see in real life, as it were. So what I've effectively done is in our torus, I've created a structure where when we are looking through the normal to the camera, it's less solid. And when we are looking through more of the double layer, we end up seeing a thicker layer. Now, this torus here is very much thinner. Okay? It's very much thinner. And this could be that it's actually just a bigger torus. What I've done in the case here, this is actually a D4D torus. Okay? So this is a D4D torus. Okay? Now, what am I saying about different thicknesses? I think this is probably the right time to introduce Matsumoto's presentation. Sorry, paper. And so here it is. And this is observation of gravity decays of multiple neutron nuclei during cold fusion. And as I said, it was submitted September the 20th, 1991. So this is over 30 years ago, my friends. And as we go down here, we have the structures. And this looks a bit like what we're simulating. So this might be our double layer on the outside. And this is the effect area. He says this is a decay of a quad neutron. Here we've got some other ones that might fall into this same kind of structure. Now, this is all published. You can go and download this on remoteview.icu. So we've got one structure here. Is this what we're looking at? I don't know. Here's another similar type structure. Here's another similar type structure. And so basically, as this thing impacts into the surface, you get more effect on the double layer that is normal to the surface than you do on the bit that's just the skin above, because you actually have a greater volume that interacts with the surface. Okay. Now, as we go down here, this is a large ring trace. As you see, it's more intense on the inside of the double layer. So this actually could be a sphere that's impacted on the surface. And what you're seeing is the effect of the double layer, or it's a very large torus. Now, I favor the fact that this could be a large torus. This is actually, I think, 200 or 400 microns across. It's quite large. And we've got some other ones here, because this one is distorted. Okay? Now, the one that I think is really interesting is these next group. These are clusters. Large numbers of clusters. But there's this one here, which I think is absolutely beautiful, because it's broken. And where it's broken, you kind of see a tube, a bit like we saw on this one. So, if I could get it to play, what happened there? We have a tube which is cut off here, okay? So, in this case, it looks like there's a tube here. So is there a tube that's going around here and it's broken and it's swung round? Okay? So could this be a torus of tori? Okay? Could this be a torus? You can see the torus at the end here moving through the material, or is this a sphere? Maybe it's a sphere. And what you're seeing here is the double layer on the sphere interacting with the surface. But this, for me, is the money shot. Look at what you are looking at here. You have a double braided structure here coming round, kind of maybe jumps off the surface here, and it's like almost like a triple braided structure here. And I believe what might have happened is it came in here and comes on to this point, and for whatever reason it dishevels here, something goes off at a different angle, and then it rejoins the surface here, having lost one of its components. And this is the splitting that I was showing you in the work of Anatoly Klimov. Okay, and again it has this thickness around the two structures that are orbiting around each other. Okay, so we've seen this physically in video and shared this here. Physically orbiting around each other, ones of different thicknesses. Now, are these tori or are they spheres? That's why we want higher resolution and higher spatial and higher time resolution. Okay. This one almost looks like it's got one in the center and then two that are orbiting around the outside. There are some traces of that type. This is a big fat one. This is one that was observed by Ken Shoulders that he never actually mentioned. Where are we? I've got the wrong slide now. Where are we? Yeah. Okay, so let's go back. And I want to read you what his description is of this. And then I want you to all collectively give Dr. Takkaki Matsumoto a round of applause for speculating, based on his research, that this is essentially what we recorded on film that I showed you earlier. So the sixth group is assemblies. I'm going to zoom that in so you can see it a bit better. Let me see if I can get that a lot bigger for you. All right, there we go. The sixth group is assemblies of widely scattered traces. Only 2 such assemblies have been observed. Many traces shown in figure 6A and 6B are distributed in very wide area. Partial traces of an assembly are shown in figure 6C and D. Strange loop-like and string-like traces are associated with the explosion, as shown in figure 6E and F, respectively. The magnitude of the sixth group is extremely large. So strange, loop-like and string-like traces are associated with the explosion. So he's saying that a ball lightning, an itonic cluster, explodes, and what you get are these loop-like, string-like traces. I think Takkaki Matsumoto deserves a round of applause. In September 1991, he published that, and we have the physical video evidence of precisely this kind of thing coming from what essentially he's describing as some form of coherent matter. Right here. This is, in my view, a string-like braided structure that's coming out of an exploding exotic vacuum object. Absolutely amazing. Amazing. Why was this guy not paid more attention to? I don't know. It's just astounding. It's just astounding how many insights he had because he just bothered to look. He just bothered to look. He did a lot of bothering though. He did a lot of work. Really. Wow. Full respect, Dr. Takkaki Matsumoto. I can't wait to talk to you. Let that day come soon. Okay. Right, so I'm assuming, for argument's sake, that it's a torus like this, okay? And if I zoom out, what I am doing is I am putting a rotational moment on it, like this, okay? Okay? But what we are looking at here is a perfect time slice. It's like frozen in time. It's like when you have wonderful light and you're taking a fast frame of some sports action or a waterfall, and it's just like it's frozen moment in time. There's no what we call motion blur. And motion blur is simulating the aperture, the camera's shutter being open for a period of time. And that is exactly what is happening, in my view, here. This is 1/60th of a second time slice. I can play it. Nah, so quick. Right, that's 1/60th of a second. That's 1/60th of a second time slice. Okay, that is 1/60th of a second time slice. That is 1/60th of a second time slice. That is 1/60th of a second time slice, and that is 1/60th of a second, and so on. Okay, I would like to see this in much smaller time slices and understand what's going on in the motion of some of these traces. Okay, so what we can do in the 3D software is we can use a thing called motion blur, but before then I have to change my luminosity, because if you're blurring the motion, you want something much more intense. So I'm going to put that back up to 5,000. So it will now be solid. So this object is now glowing, which is what these things do. You know, they glow. Why is that? Because they're condensing matter. And as they're condensing matter, they are firing out photons, which ionize the air or the nitrogen or the xenon or whatever it is around them, and they make it glow. So they cause it to glow. So I've got this glowing and it's at 5,000. It's outputting 500 times more light than is coming in, let's say, or 50 times more light than is coming in. Okay, and then what I'm going to use is I'm going to use a thing called camera motion blur, which I've already set up, so it's in a functional state for the purpose of this. And you will see something rather special as I hit this on. If I can actually find the motion blur. There we go. Watch. Hello. Hello, my friend. What are we looking at there? Let's look at the camera view, shall we? Ooh. Ooh, we like that. Oh, yeah. We like that. Yes. Brian, you can hit the drum now. What we see is something that looks a lot more interesting than just a torus. A lot more interesting than a torus. It's a helical structure, but it's not. It's a torus that has rotation around its own axis and a rotation around the common axis. And in this case, it's got an evil twin, because I haven't put the other one in there. Okay? But you can see that it has kind of repeating. So there's a repeat here, down here, and this is repeated all the way up here. But it isn't repeated exactly here. Now this one here will be repeated somewhere up here. And you see this. You see this on things like this. You've got a repeat here, a repeat here, a repeat here, but these are actually slightly rotating themselves. Okay? Now, if there was more matter in this, I would imagine that this structure here would probably repeat down here. This is a more complex structure. You might have several spheres moving around here, or tori. Okay? Or it might be interlaced structures that are spinning around. Okay? So I have this little parameter here where I'm just going to change one of the rotational components, and you'll see that we will get a very different effect. So I'm going to select this and I'm literally going to drag it down a bit. What do we get? Ooh, look at that. Oh, isn't that pretty? That's really pretty. I think the evil twin is genuinely a positron. Actually, Ken Shoulders found that he could get neutral, positron, positive and negative exotic vacuum objects. So if you can make these structures out of positrons rather than electrons, then they would move in the opposite direction given a field. Okay. So you can see here we've got a spike, 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 but these are round, round, round. And then down here we have the first of the spikes, which is the same one as up here. So what we are replicating here, just real time, is pretty much the same kind of thing here. We've got a spike, 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 but we have a curved bit here and a curved bit here. Okay, so I'm going to move this down and it's going to go even more intense. Now you get something that if you looked at it on a camera, this is our, let's say, our 60th of a second. This is our 60th of a second, the kind of thing that you are seeing here. This is our 60th of a second. And when you know that it's doing this, then this shape makes sense. It makes sense that you cannot see the whole structure like this. And it makes sense that you're not seeing... Oh, if I can actually... Oh, no. I need to click it and then go here. Right. So it makes sense that this is cut off. It makes sense that it is cut off. Because you are looking at a torus. You're looking at it side on. So I believe that this is a tori or multiple tori. Okay. I can really push this up. So we got lots of rotations. That definitely doesn't look like one torus, but it is. It is, with persistence of vision. And again, we've got this hard cut off, exactly what we see here. In fact, I'm going to put them both up on the same screen. So you can see we've got a hard angled cutoff here. Hard angled cutoff. Okay? Now, if we turn this all the way down the bottom here, we're going to get something that looks very, very familiar. Okay? What happens if we swap this out for the sphere? Now, the sphere is probably not the optimum size for this, but we'll do it anyway. Bizarrely, you get something that's a little bit not what you kind of expect. I probably need this a bit brighter because of the model here. It's probably not bright enough, this, for you. When you have very little rotation, you kind of end up with something. It's just not. It just doesn't look like a sphere. It looks like something else. Anyway, I'm gonna increase the number of rotations here, so you can start to see. You get bits sticking all the way out over here, right? And this looks like an M&M track. I don't know if you can see it, but it does from where I'm looking at it. In fact, what I'm going to do is I'm going to go into Modeler, and hopefully it doesn't break on me. I'm going to go into, just make that here. So I'll press play here so you can kind of see what it's doing. Oh, sorry, I need to actually change it to the sphere. All right. That's what the sphere is doing. That is a traveling wave. It's rotating around its own axis, and it's rotating around a common axis with an evil twin. Now what I'm going to do is I'm actually going to pause this, and I'm going to go into Modeler here. And I'm going to just shrink the size of this for the sake of... well, it helps if I don't have it on selection. Just make this a bit smaller so it's actually going to be further away from itself. So there you can see it looks a little bit more dynamic just because it's smaller. Now my trick here is I've never done this before. I'm doing this real time. Okay, do we end up with an M&M track? This would be absolutely wonderful for me if we can end up with an M&M track. Okay, so what does this look like? What does this look like when we turn the camera on? Let's just see what it looks like. I have no idea if we can make an M&M track right now. It would be absolutely a beautiful start to the year. I have no idea what we're going to see here. Oh, what does it look like? Oh, can't see anything. It's just not bright enough. It's just not bright enough. Right, I need to probably change the surface on this. Sphere. Is it going to help? No. Let's turn the motion blur off first. Is it close? I don't know. I don't know. Is it close? It's a shame it's probably not as clear on yours because YouTube is mushing it. Oh! Oh, I don't know. Maybe. I don't know. Oh, I'm going to just crank the... I'm going to crank the diffuse up ridiculously. Oh, I don't know. Is it an M&M track? It could be. It's not too far removed. Yeah. I'm on the case. I think maybe if I moved the position of the ball slightly in. Anyway, let's move it out. Let's see what we get here. I think I probably got this orbiting at too big a distance. I'm going to try and get it to do a... Oh, I don't know. It's definitely showing. Now, what you've got to... Now, what I need to do, actually, is put a black layer so that it's going into and out of a surface. And then you're going to see the gaps between the sections. So I don't know if I'm going to put this in full rotations per distance. So I'm going to make like 180. So let's do a 180 rotation here. I mean, this this kind of thing that we're doing here possibly might lead us to... This is the kind of thing that I'm trying to simulate. It's these kind of M&M tracks here, like that. What we call M&M tracks. And there's this one here with these tails. You see, you've got them in phase and anti-phase. So this is, I'm sure that this is pretty close, but maybe I've got too many rotations. I don't know. Let's try and adjust it. Let's get rid of the windows. So I don't know. Let's make that 9. Just do it so it does 90 degrees per cycle. I don't think that's doing it for me. Yeah, I think what I need to do is put a plane there, which I will do at another point rather than now. But I think you get the idea that I think maybe by taking spheres and toroids, we might be able to simulate the kind of tracks that we have been physically observing. I mean, the tracks are real. I think something like this is kind of what we need. Maybe if I switch to not the mover, the toroid turner. Okay, maybe if we change this, we can get something which is more M&M-y. No, that's not M&M-y. Well, there's. I'll tell you what. This is a caterpillar track. Right there, you got your caterpillar track. So these kind of tracks have been observed. We're back in a different phase here. So really what I want to do is put 2 control handles on here and be able to tweak them and just say what kind of track do we want to do, and well, a couple of control handles, distance from center, have more than one in there, and so on. I'm going to switch back to having the toroid in there. Let's put the toroid back. Where is it? Let's see now. See what we can do with our toroid here. That's not the one that moves. Okay, so I think you get the idea. Like I say, I just wanted to do something basic, really, for you tonight, and I think maybe we can probably get close to some of the tracks that need to be made. And as I said, you've got to imagine that these are cutting into and out of the surface. So if we go back to the one by in here, it is by Ken Shoulders. In here? Is it in here? Have I got it in here? This one? No. Where's Ken Shoulders? This one here. So this one by Ken Shoulders here. So this is probably something like did this, maybe not so complex a movement, and it's going into and out of the surface, and so it cuts its trail through the surface. Oh, and if we have no rotation, and I dialed it down, you would end up with a tube that we showed you earlier. It's just a bit too bright, this one. Anyway, this is when you need to spend some time with it, and not necessarily on a live stream. Okay, so there we go. Any questions? Yeah, I mean, John, it's not like I say, I literally thought it's about time I had a go at this, and I thought I've got 40 minutes. Let's see what I can come up with, and you know, taking what you observe in the physical recordings, or rather the recordings, the videos that we have from VEGA experiments, the tracks, and then taking that inspiration from the video description of the videos by Bogdanovich, where they're saying these clusters, they then are orbiting around their own axis and are orbiting around the common axis, and then translating across the surface. That's essentially what I've done to create this kind of movement here, and there you have it. So and I haven't added another one on here. Maybe I'll just try that. I'll just for the sake of giving it a go, whilst you talk amongst yourselves, I might just add another one on. So I'm going to clone this particular object toroid. Clone current item 1, and then we're going to move that over there. Okay, let's see what happens. Ooh, that's not exactly what I wanted. Oh no, that's okay. Is it? No, that's not what I wanted. Okay. I need to do this. Talk amongst yourselves. No, I think I'm going to do that in my own time. This is what I'm getting with two of them initially. Does it look a bit like, you know, what we had here? I don't know. Does it look a little bit like this thing? I don't know. Like a mess of stuff? I don't know. Maybe it does. Maybe it does. That's with just two of them orbiting around itself. So, okay. All right. Okay, so sphere is a spinning toroid. Yes, it could be. Yes. Could air or any element come? Yes, any element can come into the exotic state. 2D view would be M&M. Yes. To get a single strand from this, the Evo would have to be moving back and forward. No. What I'm saying is it's kind of shedding a skin as it's moving forward, or it's a sphere and it's ejecting it out the back of its pole, which we've seen in Lion, we've seen in, well, several places in Lion, we've seen in actually in the HHO work of Slobodan Stankovic, presented at ICCF 22 in Azizi. We've seen it in well, a range of different systems. So it either gets what it looks to me when I showed this at Sochi, it looks like it's consuming, and it gets too much, and it kind of like literally dumps an instance of something. Like it's a copy of itself, but it's solid matter. But the thing that's able to do the consuming and the changing from one element to another then continues on. So you have this thing: is it chucking out the pole? Is it chucking it? Is it shedding it like a lizard or a snake? These are the questions. But if we can simulate something that is able to create or do simulations and create something that has all of the observable sort of shapes in it, with just either toroid or spheres or a combination of both, in either individually or in a cluster, then I think you've got to ask yourself that's probably what's going on. In the case of the light, you're seeing it as persistence of vision for a period of time. But if we go back to, I haven't got it here immediately, maybe I can find it, but what I'm thinking here is it started to break down at this point, and or this is a whole chunk of the mesh and it just collapsed into a kind of rod. So whatever, I think Takkaki Matsumoto is correct in saying, and I'm not saying it just because I thought of it because of this, I'm saying it because that is obviously what's going on in this video, which produced this beam. And he said that is what happens when you get the explosion, you get these fragments, and the fragments produce these braided strings. Gardy Pierre, Corky, what's ball lightning? BL. BL is ball lightning. So these are the solitons. The toroid is a soliton, yes. Now the question is the toroid in the same model as we are looking here in the Paul Kollak model? Is the toroid with the toroidal and the poloidal motion fields and stuff, is that creating a sphere around it? Well, we know that, for instance, here we have this structure. Now, is this the toroid? I don't know, but what we know is that there's this hexagonal field around the structure here, which we observed, and Matsumoto observed something similar. Yes, I agree. That's what I'm saying. A Duke tree. Yes, we'll need a Boolean section through a plane. And in fact, a very, very long time ago, I used some plugins with Lightwave to actually create this. I've actually developed the technology to or the animation technology combined with some other video tools to have the thing tumbling and then leave behind the trace as it goes into and out of the surface. And I've actually created some tracks in that way. But I was doing that when I was only simulating the creation of the tracks a long time ago. In this case, this idea came after seeing the fact that these things can be caught on video, because formerly there was a lot of talk about these structures traveling at superluminal speeds, which maybe they do in some forms. The international paper is saying that they travel at up to 0.2 of the speed of light in forward motion, but clearly this here is not traveling at 0.2 of the speed of light. Nowhere near it. It's actually traveling quite slowly. Now, if it was in a higher electric field or the explosive event was bigger, then maybe it would travel at a higher velocity. But it definitely isn't traveling at these superluminal speeds. So when I was doing the original simulations of how the tracks were produced, I didn't think it would be ever possible to capture these things on the fly. And then when Bogdanovich came out in 2019, and then we started seeing our own video evidence like in 2020, 2021, then I go, well, we can do it with persistence of vision. But then that leaves me wanting to get one of these Kronos cameras, which we might get, and slice this into many, many hundreds of segments so that we know that it is either one torus or one sphere that's doing the whole path, and it's a complex path, or it's 2 or 3 or however many. And I imagine for different ones, different variations of them, I'm pretty much certain that a trace like this one is 2, and they've got some interconnection. Okay, absolutely. Pretty certain. This may be 3 with one that's going straight through the middle. This is 2, and this is probably 2. This big one here is probably 2 with this kind of surface. But we know that they wet together. This again, I'm saying that this one is an evil twin. But these ones that are straight squiggly, they could just be kind of rotating, and it's just a perspective issue with the camera, and like we saw with ones that I showed earlier, they're straight squiggly. No, the phallico-solitons are where you have the north and south separated. And they are what we observed in lion in various aspects. So you get a full soliton and a phallico-soliton. Are they opened out mandarin oranges? Yeah, kind of. Yeah, you could kind of think of it like that, yeah. John Nutter, it's good software. It's fantastic what you can do. If people want to know why I moved away from 3D animation, it's because I found Lena more interesting. So I just gave all my equipment and my skills to some Indians and walked away into a different life, which was researching this. It became too easy to do certain effects. There were other software that you could click a button and you got very good hair and very good water dynamics. And it was like, I used to enjoy solving those problems, but the problems were already solved. So I thought there's a certain inevitability that everything that people want to have is going to be already in the software sooner or later. So I wanted to try and get myself my teeth into something that was a bigger problem. Let's put it like that. A bigger challenge. Well, Gordon, I was just going, in the first 1.5 hours, I was just going over a lot of previous work. He says he missed the first 1.5 hours. Of course, you can always go back and see that. Anyway, it's great to have you here, Gordon. Is the sphere hollow in the program? It's kind of like a Fresnel effect. We know from our experiments that you get a double there. Okay, and let's maybe do a little bit of review where I was at the beginning of the presentation. So I call this presentation pasta, but it's actually reconstitution. Okay, so reconstitution is where you take something that's dried out. In this case, it's the completely stripped nuclei, which may or may not be the same nuclei that went in, and then we're adding the water, which in this case is electrons, and that reconstitutes new atoms. And we talked about that material is captured, and in this particular one here, this is in the diamond, and this is about 27 microns. It's about the same scale as the FeO2 that was created multiple times in the Vega Valley, and so it's the same type of size of structure. And it has substructures on it, but we didn't go into those. But out of one of the poles, so it's eaten into the side of this piece of diamond. It's hard to cut a sphere into diamond, right? It's just hard to do that, especially when it's only 27 microns wide, okay? Just trust me, it's hard. And it's spitting out of its pole either heavier elements that it captured, which are most likely nickel, or it's synthesized something, which I probably would expect this would be calcium. Okay, but obviously John Hutcheson had observed this before, and this is inside metals, and this would be probably in the late 1970s or early 1980s. When it's cut open, you end up with these spheres cut out, and this was also observed by Takkaki Matsumoto, and you can go and see that in the freely downloadable 1-to-1, half published at the moment, copy of his Steps to Electronuclear Collapse, Steps to the Discovery of Electronuclear Collapse book, which is available on remoteview.icu, and he'd observed it in deuterated palladium. And here is our phallico-solaton, our yin and yang. This is the same kind of thing as you're effectively getting in the yin-yangs in the ultra experiments. And they overlay. This is a magnetohydrodynamic structure, and whilst it is a hydrodynamic structure in ultra, because of polar molecules being water and OH minus and H plus and so on that form in the cavitation and the charge separation, it will eventually end up being a magnetohydrodynamic structure in the ultra experiments as well. And I'm going to talk in another presentation, probably this week, about how Vachayev, in his experiments where he's creating nearly every element in the Mendeleev table, he assessed and calculated that it was 40 electron volts that's doing the transmutation. And so this is, I believe, achievable in the cohering structures within the ultrasonics. And here we have the sort of pseudo monopole structure, and in the core of the pseudo monopole you have material that is consumed in another Hutcheson experiment. This is the ball burn sample, and here you have, I think it is either diamond or silicon dioxide that's been left as the sphere that gets left over when the structure collapses. And this was where you're seeing it in cavitation in the Amasa vibrator plate, and it's either there is a phallico-solaton between these two, or it's just one that happened to travel over there. And this is our spiraling structure that we have, it would appear, replicated today. And there are breaks, and I believe the breaks are because this neutral structure that is able, which may be intensely magnetic, or is able to change the structure, the crystal structure, so that it gets picked up with the polarizer, it is ducking below the surface. It's ducking below the surface, ducking below the surface. It's exactly the same type of trace as, in fact, I'm going to go and show that because it's relevant now. It's exactly the same type of trace as was observed by here. So this one by Shoulders, which he never actually mentioned, but it's the same type of trace. So we replicated this type of motion. This is cutting through aluminium foil here, and this one here is on a steel vibrator plate from Royshin Amasa. Okay, so that is, in my view, the equivalent structure across very different systems. This is a Evo Gun System, and this one is a low frequency vibrator, about 179 hertz. And then the material that's teleported from the center of the Lion 2 comes out and it dumps a series of spheres, not just one sphere like we observe in the tungsten influenced by the HHO in Amasa's system. We get these, and they look like they're magnetically aligned, and we've seen this in other experiments like Nova. We know that the monopoles can cluster into the same type next to each other. So we've got a small one of one type here, and they're pseudo monopoles. So they kind of attract each other, and this is the opposite type. And we know that they can cluster even further than that. And you can see them here. There's 3 of the same type here clustered in this one. And here's a great 2 together. So again, this is kind of like a phallico-soliton, but it also appears to have substructures around it, producing this hexagonal shape. And you can see they overlay. This is from the inside, this is from the outside. And then we talked about this video from May the 2nd, 2016, where someone was looking at my blog on the importance potentially of spark plug water spark ignition systems. This is off Ignition Secrets, and they spotted this thing floating around on one of the frames on the surface, the wooden surface here in this frame, and that was published December the 4th, 2018, and then in May 2019 Bogdanovich published this work, which is peer-reviewed from the National Research Nuclear University, and you have the soliton moving around on the surface, and then these solitons can cluster into balls, and they actually say that this is probably the form of ball lightning, and I'm minded to agree. And so you have a soliton, and that can form field structures that form a sphere-like thing which has 2 poles. And there you end up with this pressure double layer kind of thing on the outside. So that is Paul Colleck's 1973 patent model for the ball lightning structure. And then in the Nova experiments, we had a collapsed splat of what looks like silicon dioxide on the inside of the aluminium in the Nova reactor, and it fits quite closely with the Plasmac model. And this is another splat that's on the inside of the supernova reactor, has the hexagon on the outside, and this structure. And when you compare this to the 1993 work of Takkaki Matsumoto, it is a complete dead ringer, even down to the spacing between the segments around here. So this is obviously a quantized structure that it likes to sit in and achieve the same structure. Then I talked about the fact that if you have things orbiting around each other, not only could you get a bead string being delivered, you could also get a bead string of 2, and this actually has a rotational motion on it as it's moving around as well. And then we talked about these various structures. I'm out of order from the way I presented it earlier. And so here you have the positive material in the middle. These would be your ions, and here is your electron sheath around the outside forming your double layer. And this is from 2001 Journal of Plasma and Research, Fusion Research, and this is the double layer formation and surface tension in plasmas for balls of fire from that 2001 paper. And so your ions are in there, trapped inside, and you have your electron sheath around the outside. And this is a spherical one. This is a spherical one in a... This is actually in an Indian guy. I think he used some razor blades, some sort of like 1 rupee razor blades, and a PET bottle and some water and some table salt. And this is a hypodermic needle, and he managed to create that probably for the sum total of, I don't know, 10 to 15 rupees with a car battery, if you already had one. So he was able to create the same thing that we've been able to create, in this case Henk, on this nickel foil. Okay. And so here we have the spheres being dumped in the channels. As it's consumed matter, it then dies, the plasmoid dies, leaving a sphere, and the spheres are where you get the transmuted elements. Here's the spheres forming, and then out of the pole you get the carbon. Here's a bigger one, and you've got a lot of carbon because carbon's only 12 or 13 nucleons for the stable elements, and you've got 204, 206, 7, and 8 for lead, and this is a lead ball, and here's one where it's got a hole here. And then we show transmutation with oxygen on copper, and the ball's moving around, and this is again equivalent to the later published work or published work in the same year by Bogdanovich. I believe these are plasmoids. I don't know whether they, as I said earlier, whether they did it instantly or later. So I'm looking to revisit this, and because I actually want to try and take this picture again to see if these things have moved around the surface anymore, and if they've done any more transmutation, because that would be really freaking interesting. And then we talked about our old friend here with our dumping our alpha conjugate nuclei, then out to carbon, and so on. And so this is my thesis, is that it can collect a lot of material and then it can dump it out behind it. Okay. And here's an example on a tungsten inside of a tokamak, and you have your 5 point here, and it's breaking out and it's consuming matter, and then it's splitting off again. So this is what you get, and I believe that this may be your kind of like tree of life. And why? Because it tends to produce the elements for life, like carbon and calcium and potassium and so forth. And here's a replication here. And then this is one again in the a Mars gas on titanium and interacting with polytetrafluoroethylene, which is just carbon and fluorine. And I chose that because I believe fluorine and carbon are very important fuels for LENR. And the plasmoid is burrowing in here, and it's producing all the elements that we like in our bodies. And you can see that it is a typical plasmoid diameter that's eating in and consuming material. And it's so 20 microns wide here. And then I believe that it exploded here, which did all the other funky business. Here is your Solaton structure. So this is either a half Solaton or full Solaton. We've seen half Solaton. We've seen the both types in water. This is on tungsten. This is on the 10 yen coin. This is in the Parkhomov 225-day reactor, and this is again from Ignition Secrets. And so this is another example where there's a sphere like a magma chamber, and here, this is under here, this is the hollow structures where the nuclear reactions take place, and out of indium, which is a relatively heavy element, it's spewing out carbon and silicon and stuff. Okay, so that was the presentation, and then what we did was we did some simulations, and I actually have a previous version of the scene which I can probably load, which won't be so messed up. Okay, did I mess it up? Okay, this looks okay. And maybe I can render that VPR. So we did a simulation using this torus to create something that's similar to some of the tracks that we have seen. And by playing with the distance from the common center and the size of the torus and the rotation around its own axis and the common axis and the distance of travel in a period of time, I believe that and doing this to the nth degree, because we know from Shoulder's work we can get bead chains. And we also have seen this in Matsumoto's work. In fact, you can see the bead chain of bead chains. If I go back to Matsumoto's work, which is here, which we also discussed, he produces these spirals. This is a triple spiral, which does something here, and then it rejoins the surface here and becomes a single spiral. Interestingly, if you follow it down here, it looks like a single track coming in. Now, you know, is maybe it broke at this point, and one bit went off here with double track, and then another one kind of followed down the channel and made this track down here. I don't know. But he specifically said in 1991, so sorry, this is kind of like a bead chain. So you've got a cluster of tori here. So you've actually got these tori that are formed a cluster. And these things themselves are attracted to each other in form bead chains, and we've seen this on other experiments like Ken Shoulders has. But his description here, which is the money shot, is strange loop-like and string-like traces are associated with the explosion. Okay, there we go. So that's basically it. That is, he's saying what we have captured now on video, and producing traces which are nigh on identical, and that the frozen structure is like we showed here. He says, there we go. So that was essentially it. So it was a simulation of we were trying to simulate something along these lines to create those things, and we had the ability to change in the, oh god, it's a lot of panels. When I used to do Lightwave, I enjoyed having many screens because you could put these panels on all kinds of different screens. Yes. We'll put the graph editor up here. Now, which one are we on? Rotation. So this one here. If we remove this one, we'll get a different output. Yeah. So this is the kind of structure. So if I actually, I put this on perspective and I move around, and maybe rotate here, you can see this from different angles. Now, what does this start to look like? I should have done this earlier. What does this look like, guys? Tell me what this looks like. Oh dear. Does it look a bit like that, my friends? Does it look a bit like that? Oh, love it. It's great when you have a hypothesis and it works. Does it look a bit like that, my friends? Does it look a bit like that? Oh dear. Let's move it back a bit. There we go. Boing, boing, boing. Love it. I love it when a plan comes together. Okay, so I'm gonna read your questions here, and then I'm gonna call it a night. We got some really exciting stuff to get to you guys this year, and you know, I do believe that the Vega Valley behind me, this thing over here, if you can see where it is up here, that is the single most rich structure that's ever been recorded by plasma, that's been made by plasma. I'd like someone to see if they can find something that's more interesting and tells you more about self-organized plasma than that does, that's ever been made by anyone. And so congratulations, Henk, on that, and it's been a real pleasure. And so I'm looking forward to getting the book out. Some really great work on ultrasonic driven HHO generation by Dave, and also on supertube and discharge and working towards magnetic pickups of those things. And so there's all kinds of ideas that I'm looking forward to delivering the hard data on this year. And so there we go. Okay. See if I can catch any of your questions. Does this spell the doom of the standard model? It certainly spells the doom of people that say you can't do nuclear reactions at low energy. I mean, we are literally absolutely seeing things which we can be repeating here. And the aftermath is like the torus, that beautiful torus of iron on a copper oxide bed. It's like so beautiful. It's like and we can physically see these things on the video, it's like you've actually got something you can look at every day in the SEM, and it's going to tell you the same story every time you look at it. And you've got the videos, and the videos are telling you what it's doing, and it's kind of like, well, that is reality. How did reality happen? And it doesn't matter what your equations are. It's got to show what reality did. And it seems to be transmuting matter. And I think that when I walk through the Vachayev work, which I'll try and do at some point next week, you'll see that this has been known for some time. That you can transmute elements at low energy. Can bismuth be used to control it? It absorbs heat. If it's presenting as magnetic, potentially, but all elements can be destroyed by this. But yeah, I mean, the field fall off in it appears to be extremely like on or off. It's like an event horizon. So if you're firing these things into bismuth, it maybe it will reflect it. I've got a lot of things to think about bismuth. It is obviously the most diamagnetic element by far. Are you guys afraid of the new state? Okay, so firstly, as it was I realised in early 2017, the technology has largely been weaponized, and all next generation military devices will be using aspects of this technology, and you can see that very clearly from the applications that were decided that they were good. I think even by the end of last year, they'd put them on various warplanes. So my concern is that the different groups that have got this technology want to have a theatre to give it a go and see what happens when they use it. But it's been used before, as I've said. It was used in June in Syria in 2017, and it was probably first tested in Panama. So my point being is I could have walked away from the field or tried to make sure that people realised that this is a reality and that there are real benefits that can be had from it, and focus on those aspects. Being public about this is not going to change those bad actors in the world that are moving to use this in nefarious ways. You've always got stupid everywhere. There's always stupid everywhere. Okay. Yes, Corky, yes, you can refer to the bismuth and exploding impact studies. Thumper Hunts, yes. We've already got viewing windows on the reactors, and so we just need the camera now. So that is in the works. I'm hoping in a few weeks' time we can have some high frame rate images. Maybe a couple of months' time. Depends. Plasma makes up 99% of the matter in the universe. I would agree for the visible matter, yes, not for necessarily the dark matter. That's from Gordon Doherty. These things do emit X-rays, but they are generally at 2 kiloelectron volts or lower, and almost anything will stop that. I would be more worried about the actual neutral EVOs that, for instance, Shishkin calls string vortex solitons, coming out and then dumping them atoms and explode. When they explode, they emit electrons moving at about 10 kiloelectron volts. That's probably that's when they can do their damage, really. But the X-rays are not so penetrating. I mean, when they explode, they can emit X-rays up to 130 keV, and those are dangerous. Over 120 keV, and these been observed since Barkla in the 1910s. He called them J radiation. You know what? I kind of like the fact, I say it often, that there's a small audience, and I like the fact that working with the same audience all the time, I don't have to explain everything every time, because it is very complex. And so I respect people that have taken the time to go through, say, the last 3 years or videos since 2017 and go through the learning process, even the things that were wrong and so forth. But I think we're at a wonderful position this year, and things are going to move like they moved very, very fast the last year or two, even without being able to move around. But I'm quite excited with what their next year will bring this year. Yeah, Stephen, I agree with you. Do not try and over-cavitate things. It's fast track to not being alive. Corky, absolutely. This is the path to abundance. It's also the path to being clean with our nuclear waste. Gordon, so if I generate a plasma, it's a micro sun? Probably, yes. I think it's more likely that the sun works in the same way that this technology works, because that is what I think. Everything lines up. You don't have to really complicate matters to try and work out how it works. Yes, Corky, sound is effectively a shield for safe Evo focusing. Yeah, kind of. Yeah, it's a way to build the Evos in location. Well, blood is a kind of plasma because it's got sodium ions running around in there, so it has, the ability to conduct electricity. If you've got a ability for ions to move around, you've got electricity to flow, so the electrons are having to move. Okay. Bob, show the non-blurred version. What are we talking about here? Do you mean that? Are we talking about this? I can go here and show the texture shaded animation here. Maybe that's what you mean. I need to turn on the right object. Oh dear, I need more screens. No, I don't want a graph editor. I want scene editor. Scene editor. Where are you hiding? Over there. Okay. I want the toroid on here, not the sphere. Goodbye, sphere. Yeah. Is this what you mean? It's about perspective. In fact, I need to make this out to more. You see how it works? That's how it works. So if we go here, and we go back to our VPR. Could neutrinos be fermionic boson that become dark and light state polariton condensate? Well, there's many views on how this forms. That it forms is a certainty. How exactly it forms, there's different views. But we know we have to have something that is able to contain the ions and transport them. And some people believe it's a controlled condensate of cold neutrinos. Some believe it's itonic clusters. Some believe it's just the electron condensate. Right now, I'm minded to agree with Matsumoto, because when you collapse matter, so for instance, if you've got, say you've got deuterium, the deuteron in the center, the proton and the neutron has an electron, okay? And what happens when you crush that, if you imagine this is in isolation, but it's actually in a macro cluster, but what happens is you've already got a proton and an electron. They balance the charge out, and that makes your atom. When then that gets compressed, you get polarization of the proton, and it emits a positron and a neutrino. And then you have a positron, an electron, and a neutrino, and the positron and the electron get bound to the neutrino, and that is called the iton. And in the center, you have a dineutron. You have a dineutron which is held in an iton. And whatever matter you start with, you're always going to have at least a proton and an electron, which means you're going to end up with a neutron and an iton. So it works across every single element in the periodic table, because the neutrons are always neutrons. So like when you get above, say, calcium 40, you start to need extra neutrons to stabilize the nucleus, but the neutrons are still going to be neutrons. And so I think in Adamenko's work, they had clusters coming out which had an electronic something encapsulating something that had 5,000 to 7,000 neutron charges, neutron masses. And you can go and see this in his book, and I think in the 2003-2006 paper with Vladimir Vysotsky. So how do you get 7,000 neutron clusters in the center of this thing? Well, Matsumoto effectively explains that. And so the fact that Takkaki Matsumoto had that inspiration in 1989 is incredible. It's just incredible. Of course, he thought at the start it was like two deuterons come together and they form a quad neutron. It's the quad neutron that's exploding. And that's what I was showing you in this paper earlier today. But he realized it was many nuclei are coming together and not necessarily protium or deuterium. Can be almost anything. And when you know that the subunit is quad neutrons, and that then when you have two deuterons and they produce a quad neutron, you always have two electrons and two protons and two neutrinos. And so that is a dual iton, an I2. And when that whole thing breaks down, it ends up breaking down to helium and whatever else. He does all the calculations, but the net result is you do not see the gamma radiation, and you get different branching ratios than you would normally get predicted from hot fusion. Those commentaries are already in the published papers on remoteview.icu. So I just skipped past it, but someone says, has anyone captured EVOs off cavitation? Yes, that is the fuel of Suhas Ralkar. He had 1.5, 1.5, and 1.5 kilowatts ultrasonic horns at 19.46 kilohertz, and they were going into a mix of fuel. Now, his point of doing that was to use tungsten to mill the nickel and the other elements in there down to a 5 micron or less size, so that was resonant or the target size for his reactor. He was just thinking about sound resonance rather than anything else. Okay. What he didn't realize is that when he gave that fuel to me, which was able to very readily destroy the container it was giving him, because something was coming out and shredding that container. When I observed that in 2017, that was the first time I witnessed strange radiation. I caught it on film that was masked, on and on the actual physical material of the container, on material that was displaced from it, and also on a CCD, on a 910 Logitech web camera, which was masked. And so in those different instances, that was the first experience for me of capturing strange radiation. What that told me is that macro clusters of EVOs had stored themselves in the metal, but some of them, just with the ambient excitement in the air or thermal excitement, had got to a point of being unstable. They blew up and they shot out the strange radiation, which I captured in those various different detection methods. And so that was my first respect with the fact that Shoulders said you can store these things in metals indefinitely. Well, yes, that's true. But if they're excited too much, then they blow up. And Ken Shoulders said that I can excite them. I can store them in there indefinitely. And then if I excite them, they can blow up. And this is exactly what I observed with Suhas Ralkar's fuel in 2017. So John Nada says, does Bob think EVOs have been weaponized as projectiles or as energy sources? I think probably both. I think certainly they are. If you go and look at the Lockheed Martin coherent matter waves patent awarded in 2013, they are literally saying this creates coherent matter particle beam weapons, amongst other things. Guardian Pierre, could these iton neutrino pairs lead to muonic fusion? No. If you want to know what they lead to, it's all extremely well detailed in Steps to the Discovery of Electronuclear Collapse, which you can get from remoteview.icu, and look for Takkaki Matsumoto on there, and you can download. Half of the book is published now. It was originally made in 1999. I like it. Safe fusion. Lovely. Have you warped metal? I haven't personally done it, no. Hutcheson always kept his different distance from his devices. It was like worked behind a wall of metal and aluminium sheet. How strong of an explosion? You can go and see, I did a presentation on fluidized electrons, but there is a paper by the same name by Ken Shoulders. You cannot even imagine the intensity of the explosion. It's phenomenal. It's way beyond most other methods. I think it's the biggest non-nuclear explosion, as in fission or fusion in that sense, because it's effectively a Coulombic explosion. And maybe people are familiar with the Coulombic explosion between, for instance, a mixture of sodium and potassium going into water. That is a Coulombic explosion, but you can imagine that when you have these fluidized electrons, it's far more intense. Yes, they probably are, Corky. Evo stored in Pumapunku and magnetic stone, yes. Is strange radiation higher than gamma radiation? It's completely different. It's a cluster, and not always a predictable what's in the cluster. The typical sizes that are coming out of a range of devices explored by Shishkin et al. At Dubna between 2009 and 2018, the energy in terms of grays, I can't remember it offhand, but you can go and see a new type of penetrating radiation on the MFMP's YouTube channel, and the energy of the particles that are ejected from the disheveling neutral clusters are, as I already spoke about the electrons, they're up to sort of 10 kiloelectron volts, but the particles come out with the kinetic energy sufficient to destroy red blood cells and to cause genetic damage in white blood cells. Yeah, plasma thruster jetpacks, but there's several different ways you can use this to do propulsion, and you can actually rectify mass, so you don't need to actually. It's like reactionless propulsion. You're dragging yourself through the ether. There's a couple of ways you can do it. Ken Shoulders described one clearly. Okay, it is 1:45 in the morning for me. Thank you for joining me today, and I've been wanting to do this simulation. You know, I don't think I ever showed the simulation of how you can make the tracks on material, and maybe I'm going to combine the two techniques. At the time, I was confused really as to whether this was just one toroidal soliton, but it's clear from the work of Henk and Dave that we've extracted out of those videos that it is a wide array of forms, but in part it's just to do with the periodicity of the structures, and how that is seen from the camera angle. So you're getting something, you know, like this, or this doesn't. This is a straight torus moving without any rotational velocity relative to the camera, and rotation around itself. But this has a little bit, and you know, this is a lot more complicated. But I think we'll be able to replicate these just as on this live for the first time, real time. We replicated a number of the shapes that we've seen. So. You know, it's a real pleasure to have thought of a way to do this, and finally, after months and months and months, just actually sitting down for 40 minutes and throwing it in there, and it just delivers. So, you know, it's kind of. I said, like, when this journey is over, just everyone's going to know, oh, that's how it works, and it's just going to be. It's going to be as simple for people to think about as the internal combustion engine. You know, the basics of it, or it's just going to be really basic to understand. In many respects, more basic than a lot of the massively complex systems that are trying to be built to solve the energy problem. It's just really simple, and I think it's a combination of its sheer unbelievability and its simplicity that's probably kept it hidden, because people couldn't believe that it was that easy. I mean, that. Matsumoto's lead wire experiment, I mean, it's literally minutes to set up, seconds to do. Obviously the analysis is a lot of work, but ultra experiments are very, very short. Relatively speaking, to do a bad Vachaev experiment is probably quite easy as well. At the basis of it, the HHO experiments and those with vibration including are really rather simple and could have been done by many cultures. over many years. Certainly vibrating water could have been done by pretty much anyone. So, you know, it's just wonderful. I will do EBB. Okay, there's one from Charlie here. Is there any way? Is there a way to only make one element from the EVOs from the cavitation of water, like tune it to make more hydrogen for HHO generators? So, if you start off with heavier elements, you're going to get some, as light elements are synthesized, you're going to get protons produced. Why? Because elements that are stable for long enough are sometimes ejected from the macro cluster. This is discussed in Adamenko's book. And the most likely stable nuclei to be formed is a single proton, isn't it? It's just statistically easier, and also it gets left over from experiments, so it's kind of like a leftover, like helium's left over. If you've got a spare proton around, it's going to get left over, so you're going to get some production of that. We have seen examples where pure silver was made, where pure copper was made in an ultra experiment, pure ultrasonic experiment, and in this one, a diamond structure that I referred to a number of times. So yes, and this is where I would like to spend a lot of time with different thicknesses of aluminium and ultrasonics and an SEM, and do cycle after cycle after cycle, because it builds over time, and so you want to know when to stop. It's like if you bake something for too long, it's not edible, right? You want to stop when you want to stop. So this is an accretive process, and yeah, so it's about finding the stop point. It's knowing when to stop. It's like every artist has to know when to stop, and when the nuclear artists know how to use this work to its full, they will have to know when to stop, and less is more. Often less is more when you're creating, and this is definitely the case where less is more. Klapat, yes, EVOs are the answer to the energy problem, absolutely, 100%. The lead wire experiment is in the papers on remoteview.icu in the Takkaki Matsumoto book. It's described, there's a diagram in there. It's extremely simple. It's basically a 1mm lead wire, some potassium hydroxide, a copper pan in a Petri dish with some deionized water, and then 220 volts and a few microseconds of pulses, and then go and have a look at what you made, which I've shown you the images of, which are kind of like these ones here, which I showed you earlier. These are some of the output from those experiments. Could we combine cold fusion, sonofusion, and graphene superconductors to drop down the energy cost of nuclear fusion? You don't need to do all that. Cold fusion occurs in sonofusion. Well, fusion occurs in sonofusion, but you don't even need to go to the levels of sonofusion. You just need to use sound and, say, aluminium in water. We've demonstrated that. That is the basis of the ultra experiments. Don't need graphene superconductors. So I think use of magnetic pulses, as was used in the Vachayev experiment, and HHO may improve that, and I'm going to be talking about that probably in my review of Vachayev's work. John Nada, yes, they probably could use this coherent matter technology at Fukushima. Yes. But then they would have to admit they've got it. So I'm saying it's what it is, and they have the proposal, and they can choose to accept it is. But this is one of the big problems, that, you know, it opens up a whole can of worms of simplicity that really all kinds of people can do it. Xenon can be produced by using HHO, in my view, and I hope to be able to do these tests at some point with a residual mass gas spectrometer, which we have at Alan's lab, but we don't have an HHO generator. That's at a different place. So I need to capture the gas and then take it back to Alan's lab, because when the tungsten fissions, it fissions, if we go down to our chart down here. So our tungsten fissions, it fissions predominantly to calcium and xenon. So we can make xenon, okay? And it's a valuable element. Sorry, I'm not showing you it here. So we saw calcium made in every single spot of the end plasmoid. And for calcium to be made as a fission reaction from tungsten, it needs to produce xenon. So there we go. So in theory, producing xenon, and that in part was my proposal for why this exploded the material away. No, I'm not suicidal. I absolutely love my life, and I love this work. You know, days like today, how could you not love it? Like you have an idea, it's in your head for a while, and you think, oh God, I'll give it a go. I've been wanting to do it for a while, and bang, first time you're able to create what you see in the real world with a very, very simple thing. And I'm pretty sure that when we get high fidelity camera on this, we're going to see that these are tori, and they're orbiting. You know, it's just what it is. It's just what it is. It's great. Love it when it works. The point is there's literally hundreds of people that know this, and the books are now published, or nearly published. And so again, this is why I like a small audience, because the small audience, they're distributed. They're distributed. And I've asked several people to clone the copy all the videos, so you know, and all the associated work. Yeah, producing xenon would be great, and it, I mean, tungsten not so. How should we put it? It's like tungsten's not that common, but it's common, and much more common than xenon. Let's put it that way. Xenon has real uses. It has uses in ionic thrust propulsion systems, obviously in lights. Anyway, so according to this, you're going to get a lot of heavier isotopes of xenon, and 136 out of it. So, of course, if you can get mostly 136, then you can produce coherent xenon. That's cool. Yeah, so I think you should go back to probably 2000. So Kipak says it would like to archive all this information and spread this knowledge. Where should I start? You can get 4K downloader and archive the site. I think it runs at less than all the videos rather. It runs at less than a gigabyte at the moment, so you can get it on a gigabyte drive. In fact, I have the whole channel archived on several hard drives. It's also mirrored to all the videos that are under 2 hours are mirrored to Odyssey at the moment. So we have a backup channel on Odyssey. Yeah, so there we go. All right, so thank you very much. I'm looking forward to this year. Yes, I want to understand the machines that create the vibration for cavitation. It's piezo, PZT on a slab of metal. That's basically it, and it's just where the resonant nodes occur. And any vibration will do, any cavitation will do, but I think there are probably ways you can improve that. So thank you very, very much for your time, and I will see you soon. Have a wonderful start to the new year if you haven't already. And this is going to be a beautiful year. I really believe that. I think the nonsense is over for all those that are paying attention. It was predictably they're going to be that way. And we are hopefully going to be able to get back to the glorious march of humanity and be able to use this technology to deliver a world of abundance and protect our biosphere and live in harmony with the other species that occupy it without having to do it in a nefarious way. And moreover, this is our tool set to leave this planet and explore the heavens and terraform and enjoy the rest of the universe. We have thousands of years of discovery ahead of us, and I'm so excited for the future of humanity. So with that, I'll say thank you very much. Good night from me, and good day wherever you are, and I'll see you in the next stream. Bye-bye for now.